Coding algorithms in Python. Step-by-step coding algorithms form the backbone of modern computing, enabling everything from simple calculations to complex machine learning models. At the heart of programming lies the ability to design efficient solutions to problems through precise logical steps. Python offers a powerful yet accessible platform for implementing algorithms due to its clean syntax and rich standard libraries. Understanding how to code algorithms effectively opens doors to innovation across industries. The fundamentals of algorithm design. An algorithm is a finite sequence of instructions designed to solve a problem or perform a computation. Its correctness depends on adhering strictly to defined rules and procedures. Efficiency becomes critical when dealing with large datasets or performance-sensitive tasks. Optimizing space complexity alongside time complexity ensures scalable solutions. 3 core principles guide effective algorithm development. Correctness. An algorithm must always produce accurate results regardless of input size. Readability. Clear implementation makes debugging and future modifications easier. Performance. Balancing computational resources helps avoid bottlenecks in execution speed. Designing robust algorithms requires analyzing trade-offs between competing factors like memory usage and processing power. Choosing the right approach often involves benchmark testing scenarios. Sorting algorithms. Demystified sorting forms one of the most fundamental operations in computer science. Implementing basic sorting techniques provides insight into algorithmic behavior patterns. Bubble sort works by repeatedly swapping adjacent elements if they're out of order. While conceptually simple, it performs poorly on larger datasets compared to optimized alternatives. Quicksort employs a divide-and-conquer strategy by selecting a pivot element and partitioning the array around it. On average, it achieves O(n log n) time complexity with minimal auxiliary space requirements. Merge sort guarantees stable sorting through recursive splitting and merging phases. Although it uses additional memory, its predictable performance makes it ideal for certain applications. Search algorithms and their applications. Efficient searching mechanisms enable rapid data retrieval in programs ranging from web servers to embedded systems. 2 primary approaches dominate this domain. Linear search sequentially examines each item until finding a match. It's straightforward but inefficient for unsorted collections containing thousands of elements. Binary search excels in sorted arrays by eliminating half the dataset after each comparison. Starts at midpoint, compares target with middle element, narrows range based on comparison result, continues recursively until found or exhausted. This logarithmic runtime significantly improves performance over linear approaches, making it essential for database indexing and other high-speed querying scenarios. Data structures. For efficient implementation, selecting appropriate data structures enhances algorithm effectiveness dramatically. Different structures excel at specific types of operations. Arrays provide constant time access but require contiguous memory allocation. Lists maintain sequential order while allowing dynamic resizing capabilities. Trees offer hierarchical organization through parent-child relationships. Binary trees particularly benefit binary search implementations through structured navigation paths. Graphs represent connections between nodes via edges, forming versatile frameworks for network analysis and pathfinding problems alike. Recursion versus iteration debate. Recursive functions call themselves with modified parameters, creating elegant solutions for naturally recursive problems like factorial computation. Iteration uses loops to repeat actions until conditions change, generally consuming less stack memory than deep recursion stacks. Considerations when choosing between them include maximum recursion depth limitations in languages like Python, differences in readability between nested loop constructs and function calls, variations in cache utilization affecting overall performance. Sometimes hybrid approaches combining both paradigms yield optimal results, leveraging strengths of each technique appropriately. Dynamic programming mastery. Dynamic programming solves complex problems by breaking them into overlapping subproblems. Memoization stores computed results to avoid redundant work. Fibonacci sequence calculation demonstrates this principle well, Storing intermediate values prevents exponential time growth. Knapsack problems exemplify where DP shines by systematically evaluating combinations of items within capacity constraints. Longest common substring identification benefits from tabulation approaches that build up partial results incrementally. Greedy algorithms explained these algorithms make locally optimal choices at each stage, hoping to reach global optimum solutions. However, they don't always guarantee perfect results. Huffman coding utilizes greedy methodology to compress data efficiently by assigning shorter codes to frequently occurring symbols. Minimum spanning tree construction employs Kruskal's or Prim's algorithms, which prioritize smallest edge weights during selection processes. Scheduling jobs with deadlines presents challenges where greedy strategies sometimes fail despite appearing reasonable intuitively. Algorithm optimization techniques profiling tools help identify performance bottlenecks before attempting optimizations. Focusing effort on critical paths yields better returns than premature micro-optimizations. Leveraging built-in language features often outperforms hand-coded equivalents due to compiler-level optimizations implemented internally. Common optimization patterns include loop unrolling to reduce control flow overhead, caching frequently accessed data in memory, pipelining operations that can run concurrently. Trade-off analyses become essential when considering whether increased time complexity brings sufficient gains in functionality or scalability. Case studies in real-world application: airlines employ advanced routing algorithms daily to optimize flight schedules while minimizing delays. These systems handle vast amounts of interconnected variables simultaneously. Recommendation engines use collaborative filtering algorithms to suggest products or content personalized to individual preferences based on historical interactions. In healthcare, AI-driven diagnostic tools apply pattern recognition algorithms trained on massive medical imaging databases to detect anomalies faster than human radiologists alone could achieve. Blockchain technology relies heavily on cryptographic hash functions combined with consensus algorithms, ensuring secure decentralized ledger maintenance across distributed networks. Tools for algorithm development: integrated development environments, IDEs, provide visualization aids helping programmers understand algorithm behavior visually through debuggers and profiling tools. Unit testing frameworks automate verification of algorithmic correctness against known test cases, reducing manual validation efforts substantially. Version control systems track changes made to algorithms over time, facilitating collaboration among teams working on complex projects requiring iterative improvements. Performance monitoring utilities measure execution times under varying load conditions, revealing potential inefficiencies hidden within seemingly correct codebases. Future trends in algorithm research: quantum computing promises revolutionary shifts by enabling parallel exploration of solution spaces previously considered impossible to traverse classically. Neural architecture search automates discovery of novel network designs capable of achieving state-of-the-art results without manual intervention from researchers. Emerging areas show exciting possibilities. Automated theorem proving using symbolic logic processors, federated learning architectures preserving privacy while training models across distributed devices, multi-agent. Reinforcement learning tackling cooperative game theory puzzles, staying informed about evolving research directions empowers developers to adopt cutting-edge methodologies, enhancing software quality continuously. Conclusion: coding algorithms remains an ever-evolving discipline shaped by technological advancements and increasing demands placed upon modern software solutions. To stay competitive in today's rapidly changing tech landscape, programmers must cultivate strong foundational knowledge while remaining open to exploring new frontiers in algorithm design and implementation practices regularly.